Let's start this second part here with an explanation of how we get to respiratory alkalosis and respiratory acidosis simply by either hyper or hypoventilating. So what's behind all of this is that when you are exhaling, then you are getting rid of a waste product from your metabolism, from your aerobic respiration, that is CO2. So this CO2-rich blood is transported back to the lungs, and as you're picking up the oxygen, CO2 will go down its concentration gradient too, and it will leave the blood and go into the alveoli, and you're breathing it out. Now, CO2, when it comes in contact with water, to some degree, not all of the molecules, but enough, they will form carbonic acid, and that's this stuff here. H2CO3 is carbonic acid. And carbonic acid is rather unstable, and it falls pretty much right away apart into hydrogen ions plus bicarbonate ions, these guys here. Now note that I drew these arrows reversibly. That means if we are getting rid of a lot of CO2 because we're hyperventilating, so CO2 out, we get rid of it, that means we're pushing the equation in the direction toward, well, making more carbonic acid because we're getting rid of CO2, and that falls apart into water and CO2, and we're getting rid constantly of the CO2. So that's why if we are hyperventilating and we're getting rid of too much CO2, then we are going to increase our pH because we're losing hydrogen ions, because these hydrogen ions are necessary to get together with bicarbonate ions to make carbonic acid and then fall apart into water and CO2 because we're constantly breathing this out. So respiratory alkalosis comes about from hyperventilation. Think of CO2 as an acid, and literally when it comes in contact with water, then it will form carbonic acid, and it is an acid. It is exactly what the name says. So, in other words, if you're hyperventilating, you're getting rid of an acid, too much of the acid CO2, and that leads you to a respiratory alkalosis. That means your blood pH will start to be on the rise. You might think, wow, no big deal. Well, you should try it. Try to hyperventilate for about 10 seconds and see how you feel. Because even in these 10 seconds, you're getting rid of too much CO2 already, and your brainstem will measure the very slight but measurable change in the pH, and it will cause you to feel very dizzy. And if you continue, you will pass out. So try this please only for about 10 seconds, but see how you feel when you're hyperventilating and that dizziness that comes about it. It's because you're shifting your blood pH slightly but measurable, and your body's freaking out. When you are doing hypoventilation, let's say you decide I'm going to hold my breath and I don't want to breathe anymore, it's too much work, then you are running into the opposite problem. If you're hypoventilating, you're keeping all of that CO2 in your body. So now the CO2 stays, and it combines with more and more water to carbonic acid, more and more carbonic acid, and that dissociates into hydrogen ions and bicarbonate ions. And these hydrogen ions, they will acidify your blood, and that leads to a respiratory acidosis. Now, capnia, these two terms, hypo and hypercapnia. Capnia refers to CO2 levels. So hypocapnia means I don't have enough CO2, and hypercapnia means I have too much CO2. Now let's take a look at the introduction that's given here in the lab. And so you have this old style spirometer. We have actually pretty fancy ones. And so make sure that you know the 4 volumes that are listed right here. Then here is a spirogram. It's very similar to what I put on the first page. Make sure that you know all the volumes and all the capacities. So you do need to know tidal volume, inspiratory reserve volume, expiratory reserve volume, and residual volume, those 4. And please know these. And you can either look at this graph right here to find them, or you can look at my nice drawing right there. And then moving on to the 5 capacities, we have the inspiratory capacity, that's the tidal volume plus the inspiratory reserve. The expiratory capacity is the tidal volume plus the expiratory reserve. The functional residual capacity is equal to the expiratory reserve volume plus the residual volume. The vital capacity is going to be the inspiratory reserve plus the tidal volume plus the expiratory reserve, and the total lung capacity. Then you're adding the residual volume to inspiratory and expiratory reserve and the tidal volume. So all 4 of these together. And here we have the equations, how you predict vital capacity. So you can follow exactly these formulas to estimate your vital capacity. If you're male, then your vital capacity is calculated by taking 0.052 times your height in centimeters. So you need to calculate your height in centimeters. And keep in mind, if you only know your height in inches, then how do you get from inches to centimeters? It will be inches times 2.54 is equal to centimeters. Okay, so so 0.052 times your height in centimeters minus 0.022 times your age in years minus 3.6, and that should give you your vital capacity. So if you are a young male, if you're pretty tall, you might have a vital capacity as high as 5 or 6 liters. If you are a little bit smaller, then you will have a little bit smaller vital capacity, also if you're older. Now for females, the way you calculate your vital capacity is this formula right here. You take 0.041 times your height in centimeters using the same conversion, and then you subtract 0.018 times your age in years, and then you subtract another minus 2.69. And that should give you your vital capacity. So for women, generally speaking, the vital capacity is going to be a little bit smaller, more likely close to 3.5, 4 liters, maybe 4.5, depending on your age and your height. Those are the main contributing factors. And then the lab manual keeps going into obstructive restrictive lung disease. I think we're kind of done with that. This here is the FEV1 measurement. So within 1 second, from here to here, you would measure how much of the air volume in the lungs can be breathed out. And for somebody that has normal lung capacities and everything, they should be breathing out the vast majority of what's in their lungs within 1 second. If somebody is having obstructive lung disease, keep in mind that it will take longer. It will take more like this for somebody with obstructive lung disease. And so you can scroll through the explanations. There are some explanations of how to measure these volumes and capacities, but since we don't have the equipment handy, that's fine. Here is the whole CO2 issue and aerobic respiration, so you can read up on that. And here's some more explanations, and let me scroll to where it gets important again. So here's a nice chart. This is sort of what's expected for you to generate with your own measurements. You're expected to generate some tidal volume, tidal, going right here, then inspiratory reserve, and then vital capacity all the way down, and then you can come back and do some more tidal breathing. So something like that, that's what we're expecting for you to measure with the instruments and the equipment that we have in the lab. So I've skipped down now here to the data report pages. You should fill out your profile and everything. Definitely calculate your predicted vital capacity. That's definitely something you can do at home with just simply using a calculator. Please calculate your predicted vital capacity. And in fact, we get pretty close actually with the measurements. If you inhale and exhale out of this into this tube as instructed, you should be pretty close. So you should have the predicted vital capacity. It should be from these calculations right here. And you observe vital capacity. Obviously, we weren't able to do that, but it should be fairly close. It should be somewhere, they're saying here within 80% of the predicted value. And then your measurement, your tidal volume should be fairly close to what is expected. So that will be about 0.5 liters. And then your maximum inspiratory and expiratory flow rate, you obviously weren't able to measure that. Breath period, that's how long one breath takes. So let's say we take 5 seconds for one full cycle of inhaling and exhaling. Then we would take the calculated breathing rate then would be 60 divided by 5, and that would be 12 breaths per minute. And then you can calculate, if you have the tidal volume, you can calculate the airflow rate. And so here, so now in table 12.2, you were supposed to calculate the forced expiration volumes and rates from a healthy subject at rest. You should look up what the normal resting values are for inspiratory reserve volume. That was in sort of the second and third page of this lab. And then the forced inspiratory flow rate, you don't have to do that. Vital capacity, you can use the estimated value. And forced expiratory flow rate, expiratory reserve volume, you can estimate that. This one you can skip that. And then forced expiratory volume at 1 second, you should be about 80%. You'll be able to exhale about 80% of your vital capacity with 1 second. You should definitely be right about 100% after 3 seconds. The residual volume, we said we estimate that at 1 liter. And since you don't have good numbers, you can't really calculate the FEV1 to VC ratio. So now here, compare the subject's lung volumes in milliliters with the average volumes presented. Since you don't have any measurements, please just look up what's normal for your gender and then put that in. And since you don't have any other numbers, then we'll just go with what's normal. Now let's take a look at the questions. And again, well, we would need data to really answer this here. But one thing that's interesting, so your FEV1 to VC ratio should be 80%. So you should be able to breathe out 80% of your vital capacity within 1 second, and at least 95%, so almost everything, within 3 seconds. And so these numbers, you should be, FEV1 to VC ratio should be 80% or better, and then FEV3 to a VC ratio 95% or better. And then you could take a look at these normal lung volumes. Obviously, you don't have anything to compare it to since we don't have any measurements. But here on 3, why does predicted vital capacity vary with height? Well, of course, if you're taller, then the presumption is that you have more space in your thoracic cavity. And more height means more space, and that means larger volumes. So explain how factors other than height might affect lung capacity. Well, definitely your age also plays a role, and gender, and lifestyle choices, what you're doing with your lung capacity. Also asthma, inflammatory processes, they could affect certain capacities. Now on 5, of course, a smaller person would have less vital capacity than a larger person because there's just less space. If you're smaller, then you have less volume. How would the volume measurements change if data were collected after vigorous exercise? So your tidal volume would increase, and that would take away from your expiratory and inspiratory reserve. And so those are the main things that you would see in vigorous exercise. Also, of course, increased breathing rate. That's what you see too. How do lung capacities relate to lung volumes? So capacity is a compound of more than one volume versus a lung volume measurement that's a single number. The definitions for tidal volume, inspiratory reserve, expiratory reserve, residual volume, that's all on that second or third page of your lab manual for this lab. So please look it up and put that in there. Then name the 4, it's actually 5. 5 pulmonary capacities. 5. And so there we have the vital capacity, the expiratory and inspiratory capacity, functional residual capacity, and of course the total lung capacity. And again, I'm going to refer you to that page in the beginning of this lab where everything is defined, and you can you can look it up. Define forced expiratory volume. That is the volume of air that you can get rid of out of your lungs, that you can exhale if you really try. And the most significant measurement here is the FEV1 usually, and that number is different for people that have obstructive lung disease. Okay, so here moving on to 15. Is it possible for a subject to have vital capacity within normal range, but a value of FEV1 below the normal range, well, that's asthma right there.